Find the eigenvalues and eigenvectors of the given matrix A. First of all, we should know the meaning of the term eigenvalue. A is an operator and is allowed to operate on the function x, gives some number called eigenvalue and the same function. If it is the case, we can call this one as an eigenvalue equation. Here d by dx is an operator and is allowed to operate on a function e power mx. We can get m into e power mx. Here m is the eigenvalue, e power mx is the eigenfunction. Say we are having the same logic, ax equal to lambda x. Suppose the d by dx is operating on sin x. We can get 1 into cos x. Such equation is not called as an eigenvalue equation. If it is an eigenvalue equation, after completion of the operation, we should get the same function. From this equation, this is eigenvalue equation, ax minus lambda x equal to 0. If you take x outside, we can get a minus lambda into x equal to 0. Then multiply lambda with the help of an unitary element I. This is our unitary matrix. That will not change the nature of lambda. So a minus lambda I into x equal to 0. This is called a characteristic equation. Now we have to write the characteristic equation for the given matrix. A minus lambda I into x equal to 0. Inside the determinant we have to write a minus lambda I into x equal to 0. Here the function x not equal to 0. Therefore, a minus lambda into I should be 0. See this, a minus lambda I, this is a minus lambda into this is I3, I. Then if you carry out the operation, we can get this mere matrix multiplication. So that just you have to subtract lambda from the diagonal elements. Then modulus of a minus lambda I equal to, inside the determinant we have to write 1 minus lambda 2 3 0 2 minus lambda 3 0 0 2 minus lambda. This determinant value should be 0. See this is our characteristic equation. Now take the determinant. There is 1 minus lambda, leave this column and this row, 2 minus lambda into 2 minus lambda minus 0, 0 into 3, 0, then minus 2 into, leave this column and this row, 0 into 2 minus lambda 0, minus 0 into 3, 0, so this is 0, plus 3 into, leave this column and this row, 0 into 0, 0, minus 0 into 2 minus lambda 0. Entire should equal 0 because a minus lambda equal to 0. If you simplify this, we can get 1 minus lambda into 2 minus lambda whole square equal to 0. In the above equation, either 1 minus lambda equal to 0 or 2 minus lambda whole square is equal to 0. If 1 minus lambda equal to 0, then we can get the first root lambda 1 equal to 1. This is the first eigenvalue. If 2 minus lambda whole square is equal to 0, we can write 4 plus lambda square minus 2 into 2 lambda equal to 0. A minus b whole square is equal to a square plus b square minus 2ab. This is lambda square minus 4 lambda plus 4 equal to 0. Now lambda square minus 2 lambda minus 2 lambda plus 4 is equal to 0. This minus 4 lambda is written as minus 2 lambda minus 2 lambda. Just to take with this lambda minus 2, then here take minus 2 outside. Once again you can get lambda minus 2, which is equal to 0. From this we can have lambda minus 2 into lambda minus 2 equal to 0. Then we can get two roots, lambda 2 equal to 2 and lambda 3 is also equal to 2. So the eigenvalues are lambda 1 is equal to 1, lambda 2 equal to 2 and lambda 3 is also 2. To verify whether the obtained eigenvalues are correct or not, we have to apply the rule. That is, the sum of the eigenvalues lambda 1 plus lambda 2 plus lambda 3 should equal trace of the matrix, trace of the given matrix. This is the first condition. Second condition is the product of the eigenvalues lambda 1, lambda 2, lambda 3 should equal modulus value of the given matrix. Now we have to verify. Apply the first condition, lambda 1 plus lambda 2 plus lambda 3, which is equal to 5. 1 plus 2 plus 2, that is equal to 5. Then in the given matrix take the trace. Trace means sum of the diagonal elements. This is the diagonal element. Just take the sum. 1 plus 2, 3, 3 plus 2, 5. So the trace value is also 5. So the first condition is satisfied. Now consider the second condition, the product of the eigenvalues. 1 into 2, 2, 2 into 2, 4. Then we have to take the modulus of A. A equal to 1, 2, 3, 0, 2, 3, 0, 0, 2. Just to take the determinant, that is equal to 1 into 2 into 2, 4, 4 minus 0, minus 2 into 0 minus 0, plus 3 into 0 into 0, 0 minus 0, which is equal to 4. So this is also 4. So the second condition is also satisfied. Therefore, the observed eigenvalues are correct. Now we have to go to the eigenvectors. Eigenvectors. Here the matrix is 3 by 3 in order. So we can have 3 eigenvectors. They are x1, x2 and x3. These are all corresponding to lambda 1, lambda 2 and lambda 3. Now take the general equation a into x, which is equal to lambda into x. With the help of this equation alone, we have to find out the eigenvectors. First we have to put the value of x1, that is a into x1, which is equal to lambda 1 into x1. We have to assume x1 which is equal to x1, x2, x3. Now the value of a is the given matrix 1, 2, 3, 0, 2, 3, 0, 0, 2. This is a. x1 is small x1, x2, x3. Then the value of lambda 1 is 1. Once again x1, x1, x2, x3. Now multiply, we can get x1 plus 2x2 plus 3x3. Then 0 into x1, 0 plus 2 into x2 plus 3 into x3. Here 0 into x1, 0 plus 0 into x2, 0 plus 2 into x3, 2 into x3, which is equal to x1, x2, x3. Now we can have 3 equations: x1 plus 2x2 plus 3x3, which is equal to x1. This is equation 1. Then 2x2 plus 3x3, which is equal to x2. This is equation 2. 2x3 equal to x3. This is equation 3. See here, 2x3 equal to x3. Put x3 equal to 0. So 2 into 0 is 0. Then x3 equal to 0. Here if x3 equal to 0, 2x2 equal to x2. Therefore x2 is also 0. From equation 1, x2 is 0, x3 is 0, then x1 equal to x1. We do not know the value of x1. Put x1 equal to k. Now the value of x1 eigenvector corresponding to lambda 1 is x1, x2, x3, which is equal to the value of x1 we have assumed is k, x2 value is 0, x3 value is 0. We do not know the value of k. We have to find out the value of k using the normalization condition. The normalization condition is x1 dagger x1, which is equal to 1. Using this normalization condition, we have to find the value of k. For that, see, A dagger means conjugate transpose, equal to A star transpose. See, the matrix A is 0, minus I 0. A star means just we have to change the sign of I. 0, this minus I is changed into plus I, this plus I is changed into minus I, then 0. Just we have to change the sign of I. That is complex conjugate. Then you have to make the transpose of this complex conjugate. A star transpose. This is called A dagger. A dagger equal to A star transpose. If you make the transpose, we can get this matrix. Once again, 0 minus I 0. If A star transpose, that is A dagger equal to A, such matrix is called a Hermitian. If conjugate transpose of a matrix is equal to the same matrix, such matrix is called as Hermitian. So dagger means conjugate transpose. Now come to our problem. Here x1 dagger, the value of x1 is k0 0. No item is present. So x1 dagger means mere change this column matrix into row matrix. X1 dagger is k 0 0. This is our x1 dagger. Just I have changed this column matrix into row matrix. Then x1. It is a column matrix k 0 0. This should be equal to 1. Now make the multiplication. K into k square plus 0 into 0 0 plus 0 into 0 0, which is equal to 1. K square equal to 1. Therefore k equal to 1. Let's take the positive root. Now the characteristic vector, eigenvector x1 is equal to x1 x2 x3, which is equal to k 0 0. Then this is equal to the value of k is 1 0 0. So this is eigenvector corresponding to the eigenvalue lambda 1 equal to 1. This is the first eigenvector. Now we have to find out the value of x2. For that, you have to write a into x2, which is equal to lambda into x2. Here the value of x2 is x1 x2 x3. Then this is lambda 2. The value of lambda 2 is 2. In our case, lambda 2 value is 2. Now substitute the value of the matrix A. 1 2 3 0 2 3 0 0 2. This is a matrix. Then x2 is x1 x2 x3, which is equal to lambda 2 value 2 into once again x2 x1 x2 x3. Now make the multiplication. x1 plus 2x2 plus 3x3 2x2 plus 3x3, then 2x3. We can have the equation 2 into x1. This is 2 into x2. This is 2 into x3. This is equation 4. This is 5. This is 6. Now take the equation 5. 2x2 plus 3x3 equal to 2x2. Therefore 3x3 equal to 2x2 minus 2x2, that is 0. 3x3 equal to 0. Therefore x3 equal to 0. From 5, x3 equal to 0. Then come to the equation 4. From equation for x1 plus 2x2, then the value of x3 is 0, which is equal to 2x1. So 2x2 which is equal to x1, we can have this condition, 2x2 equal to x1. Now put x2 equal to k, therefore x1 equal to 2k. Now we can have the second characteristic vector, that is eigenvector x2 equal to x1, x2, x3, which is equal to, then we have assumed the value of x1 as 2k, then x2 equal to k, the value of x3 equal to 0, but we do not know the values of 2k and k. We have to find out the value using the normalization condition. x2 dagger x2 equal to 1. This is a normalization condition. This is x2. x2 dagger is just convert this column matrix into row matrix. 2k, k, 0. This is the value of x2 dagger. Then x2 is, write down the matrix, 2k, k, 0. This is equal to 1. Now make our multiplication. This is 4k square, 2k into 2k, 4k square, k into k, k square, plus 0, which is equal to 1. That is 5k square equal to 1. K square is equal to 1 by 5. Then k equal to 1 divided by root 5. Now the value of x2 equal to x1, x2, x3, which is equal to 2k. The value of x1 is 2k, then x2 is k, x3 is 0, which is equal to 2 by root 5, because the value of k is 1 divided by root 5. So 2 into k, the value of x1 is 2 divided by root 5, then the k is 1 by root 5, then x3 is 0, x1, x2, x3. So x2 equal to 2 by root 5, 1 by root 5, 0. This is a eigenvector corresponding to the eigenvalue lambda 2 equal to 2. x3 is also having the same value because lambda 3 is also 2. So these are all the eigenvectors of the given matrix.